Hello, everybody. I hope you're doing well. Welcome to another video reviewing your probability and statistics. So today in this video, we're going to take a dive into a different topic. And this topic is called least squares. So why are we studying this topic? Well, it just so happens that sometimes in the real world, we want to do some forecasting, right? Through what's called regression analysis. So we can think of this video or this series like talking about prediction, right? Now, what do I mean by prediction? Well, let's make this a little bit more concrete. Suppose I have a business, right? And I want to be able to predict the revenue I get from selling a certain quantity of product, right? So you can imagine quantity is on the x-axis and revenue is on the y-axis, right? So I might say, for example, for quantity 100, I get some revenue 200, right? So I might get something like this. I might have, some quantity revenue here, some quantity revenue here, and so on, right? So you can imagine we have like the set of data, right? And with the set of data, I want to be able to develop a model such that given a quantity, I want to be able to predict how much revenue I can make, right? Because what this can do is maybe as a business, we might want to forecast our sales, right? And this might be a factor that we want to talk about, right? So given a quantity, predict the revenue. So let's write this problem up here. So we want to predict revenue given quantity. Now you might ask, Karthik, this might be really hard to predict the revenue given quantity. There's just too many factors in the real world, right? There might be stuff due to logistics, supply chain, there might be stuff due to the economy, etc. Well, let's keep our problem a little bit simple. Let's say that we say that quantity is the only thing that affects prediction. I know that this is not a good assumption, but let's simplify our discussion a little bit. So we want to predict revenue given quantity, right? But with this data, like I want to be able to have some mathematical function where I take in a quantity and give prediction. Here's one possible mathematical function. Maybe I can have a function that, goes through all these points, and this is my model to predict revenue given quantity, right? Now you might be like, oh, this looks too complicated, right? How on earth could somebody just come up with this model? I'm not sure that connecting all the points might be a good thing. Maybe my data could be faulty, right? So what do we do in this case? Well, instead of just fitting a model that goes through all these points, which is generally not a good idea in practice, let's have a model that kind of approximates the trend of the data, right? And to approximate the trend of the data, we notice that among these x's here, right, the x's seem to be increasing, right? So as the quantity goes up, we seem to be increasing revenue, and that is usually the case in the real world. But usually you don't want to fit like a function that goes through all these data points perfectly, right? You can imagine like if I plot like, some more x's here, right? Then I might have, something that goes like that, right? And this function might be extremely complicated to describe. This problem we're seeing here is called overfitting, right? In that you have a model that perfectly fits your data, but it's very hard to generalize, right? So poor generalizability, right? And we don't want that in our problem, right? We want to be able to have some kind of model where we can kind of generalize given unknown data, right? Or newly seen data. So overfitting is a bad thing here, right? Okay, so here, what's another way we can do this? Well, maybe we can fit like, some curve that goes like this, right? But notice the blue curve doesn't really like seem to capture our data really well. It's not really catching on to the trend. So this kind of seems what's called an underfit. So what can we do instead? Well, here's a potential solution. Let's assume that since prediction is influenced by quantity, that we have a line basically, and a quantity influences prediction, right? So here's a line that might best solve this problem, right? So we call this red line here our line of best fit, right? I what is the line that best captures this set of x's or our data really well, right? So wouldn't it be great if we had an algorithm that we could use to solve the line of best fit? So I guess our new goal for this section, right, is solve for the line of best fit. So we want to solve for the line of best fit given data. And since we assume that quantity is the only thing that can affect prediction, a linear model seems like a viable approach in this case. But now you might ask, okay, I get that we were solving for a line of best fit, but what line do we use, right? Like, what line do we use? Suppose, like, I didn't have a computer or anything, right? What line can I use to, like, perfectly fit this data, or maybe fit, like, to the best of our ability, right? So you might have something like this, right? Let's draw another picture here. So we have quantity and we have revenue, right? And our x's look something like this. So you might have a line, I can try a line that looks like this. Oh, that green line doesn't look good. Maybe I'll try another line that looks like this. Let me trace this over in blue. Here's another line I can try. Maybe I can try this line right here, right? And how do we know like which line is the best to use, right? Well, what do we have here, right? We have that a line can be expressed as mx plus as y equals mx plus b. So what is m? If you remember from your algebra class, m represents the slope of the line. It's the rise over run. So for a unit change in x, so if x changes by 1, how much does y change? That's called the slope. And this b is called the y-intercept. So when x equals 0, what is y at that point? So that's what b is. So every line can be specified as y equals mx plus b. So now you might say, well, since every line is described by a slope and an intercept, maybe I can try all possible combinations of slopes and y-intercepts, right? And just hopefully pick the line that somehow fits the best, right? By eyeballing it, right? And it looks like here, this red line seems to fit the best from an eyeball, right? But how do we know that it's indeed the best, right? So what we're going to do in this series, or this set of videos, is we're going to build up to a model or an algorithm we can use to determine what is the best line of fit, right? And what we need to do is this. Number one, we're going to frame a metric to describe how good our line is. So we want to describe how well does our proposed line fit our data set. So we need to first determine this metric, right? And then now that we have this metric, we need to do the second step. The second step involves optimize the metric. Because if we have a function that can tell us how good our line of best fit is, wouldn't it be great if we can just simply optimize that function, find indeed what's the best? So we can optimize the metric from step one. And then now that we've optimized our metric, we want to see what is the best we can do to, what is the best line to fit our data or capture the patterns in the data sets. So these three questions are steps we're going to be tackling in the following videos on linear least squares. So I just wanted to give you a brief intro as to the problem we're trying to solve. That way we're on equal footing here. So till next time, I will see you in the next video.